everyone, welcome to Representing Motion with Graphs. This is the second of the Representing Motion videos. This is super important and can be really tricky when you're first starting off reading these graphs. So this will go over how to read and convert between position, velocity, and acceleration versus time graphs. And I'll kind of just be explaining them as we go here. So let's just jump into the first question. We have a position versus time of Bob traveling is shown down here. And we're going to denote the x position with north as positive and south as negative. So we have this position versus time graph here. So this is the position that they're at, and this is the time. And we'll just assume here that this is each square is like 1 unit in meters. And then these time stamps are shown on the bottom. Alright. So the first thing it asks is when is Bob traveling north and when is he traveling south? So basically we want to know when is Bob going north and when is he going south, right? So let me just scroll down here a little bit. Alright. So we'll write our north values here and our south values. Okay, so how can we tell when is Bob traveling north and when is he traveling south, right? So we denoted north as positive and south as negative. So when is Bob traveling towards the positive direction? So if we think about what are we looking at here, this is a position graph. So let's just take this first segment here from time 0 to time 5. We see at the initial point, the position is that x equals 0, and at the final point, x equals 2, which means during this interval, Bob is traveling towards the positive direction. So that means during this first interval from 0 seconds to 5 seconds, Bob is traveling north. Alright, now let's look at this next chunk from 5 to 9. We see that at 5 he's at position 2, and at 9 he's at x position 2 as well. And during this whole time, his position is constant, so he's not traveling north or south here. Alright, so let's take our next one here. We have from 9 to 13. At point 13, he's now at x position equals 4. So he's going from 2 to 4. The position goes from 2 to 4, which is getting more positive, which means that will also be traveling north. From time equals 9 seconds to 13 seconds. Alright, so now at 16 seconds, he's now all the way down here at x equals negative 2, or negative 3. So since he's going from a large value to a small value, he's going to be traveling south, so that 13 seconds, from 13 seconds to the 16 seconds. Okay, and then at 20 he's at 0 again, which means he's again traveling north from 16 seconds to 20 seconds, and then from 20 to 25 he ends at x equals 4 again, so he's also traveling north from 20 to 25. So if we notice here that for the values, we can also look at the slope. So this slope is a positive slope, and we will soon find that the slope is the velocity. So the slope of the position is the velocity. So we know that the velocity here is positive, the velocity is positive, the velocity is negative, oops, the velocity is negative, the velocity is positive, and the velocity is positive. So that will also tell you what direction you're traveling. When the velocity is positive, it's going towards the positive direction, which in this case is north. So the next question asks, what is Bob's displacement and velocity during the time interval from 0 to 5? So displacement, we pretty much already solved for, because we know that the x initial is equal to 0 and the x final is equal to 2. So the change in x is equal to x final minus x initial, so that the change in x is equal to 2 minus 0, which equals 2 meters. That'll be the displacement. But how do we find the velocity? So we know that the velocity is a slope, but we can also go to our average velocity equation, which is the change in x over time, which we just found that it was 2. the time is from 0 to 5, which is 5 seconds. So the slope, or the velocity, will be, and this is in meters, and this is in seconds, so it'll be 0.4 meters per second. And that is the slope value of the line, but also given by this equation that we've learned about in the past. Alright, so now it's asking, when is Bob accelerating? So if we look at most of these lines here, this slope is constant on all of these parts, which means there's no acceleration. But this portion right here, the slope is changing. Right? If I go, we can see here that down here the slope is like this, and then it goes like this, and it gets steeper, which means there must be some acceleration during this portion. But everywhere else, the slope is constant along all these lines, right? Doesn't matter, the slope is constant. So during this time interval, and this time interval only, there will be some acceleration. And we can't calculate the numerical value just from this graph, but we just know that there is some positive acceleration because the velocity is increasing. So from point time 20 to time 25, we'll have some acceleration. So from 20 seconds to 25 seconds. So we want to know, okay, another question. So what is Bob's velocity at time equals 10 seconds? So let's look back here. So at 10 seconds is right around here. What is the velocity? Well, we can't, it's hard to just find what is the velocity at this exact point, right? Because we need to find like initial and final position. But since we know the velocity is the same throughout this whole interval, we can use these points to find what the velocity is. So we know that the x is 4 from 2, and the point is from 9 to 13. So if we go down and solve for that average velocity, we know that the velocity will equal the change in x over the time, or the change in time in this case. That's why we'll have that change in time. It goes from 4, the x final is 4 minus 2, and it's 13 seconds as the t final, and 9 seconds. So that'll give us 2 over 4, which is equal to 0.5 meters per second. So, and this will also be north, and I should denote this is also to the north because it's positive for both of these. And so notice that if we find the slope of this line right here, we'll have the velocity over this entire time range. So that'll be true at this point 10 and anywhere else on the line. Alright, and finally, when is Bob's speed the greatest and when is it the least? Alright, so this kind of has a lot to it. How are we going to determine when the speed is the greatest and when the speed is the least? Well, if we scroll up here, we know that we can find the speed of each of these segments pretty easily. We already determined that it's the velocity, right? And since speed is just the magnitude of the velocity, we don't care what the direction is, we just care about the value. So we can just go through each one of these and find where is the speed the greatest and where the speed is the least. Sorry. So from 0 to 5, we already determined that the velocity, I'll do all of these in this green color. So for this first point, we have velocity equals the change in distance, which is 2, over the time, which is 5. So that'll be about 0.4. Now at this point here, the velocity is equal to the change in distance, which is 2 minus 2 over this 4 seconds, but that's 0 because the slope is flat. So this will have 0 meters per second. So since speed is just the magnitude, you can't have any less than 0. So we know this point will be the least. But let's just keep going through these. So this velocity here will be from 4 minus 2, which is 2, over this time range, which is 4. So that would be 0.5. Now this time range right here, we have a velocity which is equal to the change in x. So this is the final point at -3, and the initial point is at 4. So we'll have -3 minus 4 over 16 minus 13, which is just 3. And that'll be -7 over 3. And since we're trying to find the speed, this is meters per second, we can just say 7 over 3 meters per second. So that's the largest so far. If we go down and check this one, we have the velocity equaling to 2 minus a negative 3, which is 3 over 4. And then I'm just gonna disclude this part. We'll say we're only trying to find up to point 20 because we can't find every exact velocity point here. So for right now, we will just say up to the 20-second mark, what is the greatest and what's the least. So if we look at all these velocities we found, this one is the greatest, since it is 7 over 3, which is larger than the other ones. And since we're just looking at speed, this one will be the least. Alright, so I could write that then, but I think that's good. Alright, so let's look at the next one. So let's look at sketching some graphs here. So we're given this position versus time graph, and we need to sketch the velocity and the acceleration versus time graphs. Alright, so we know that the velocity is the slope of the position, right? So let's try to sketch out this graph here. So let's just take it segment by segment. So we already found these slopes in the previous equation. So we know that this one was, what was this one actually? This one was 0.4 meters per second. So we know that's the velocity already because we already found what the slope was. So since it's constant throughout this entire interval, we can just draw a straight line, and this is noted as 1, so it'll probably be somewhere around here, as like right here. So this will be a constant line right here at 0.4. Alright, and then this one, since this slope is 0 from these 2 points, the velocity will be equal to 0. So this one will just be a straight line down here, which will be like that. And we can just continue doing the same thing for this one. So this one we already found was 2 over 4, so that's 1/2. So we can draw the velocity 1/2 right here, that's constant. Alright, now this one right here, we found that this one was, what, 7 over 3? So 7 over 3, so that's a little more than 2. But since it's now, this one is actually a negative 7 over 3. It's going down. So when we're drawing it on the velocity graph, we'll have to draw it below this x-axis because we're assuming the positive is in the same positive direction. So this one will be about 1, 2.5 or so, right down here. And this should be straight lines with no slope, but it's hard to draw. And then this one right here, what did we find this one to be? This one was 3 over 4. The slope of this is 3 over 4. So from 16 to 13, the slope will be right around here. And then this one right here, so this has a changing velocity, as we kind of drew out in the last time. It starts off with the slopes being light, and then they increase as the graph goes on. So we're going to assume that this is constant acceleration here. And so when it starts, it looks like it starts out pretty much at 0. So we can start our line from 0 and increase the velocity as we're going. So when there's this slope here, we can start it at 0 and have it increasing like this until it gets to 25. And we'll say that is the velocity graph there. It starts at 0 and is increasing, which is showing some acceleration. So now if we want to sketch the acceleration graph, we just need to find the slopes of the velocity graph now. So at all these points here, at all these points, the slope, which is now equal to acceleration, is 0. And all these 0, and we already answered that in the last example, that all these points are 0. But this one does have an acceleration, which we can quickly solve for if we say that the acceleration is the change in velocity over time. It ends at, we'll say 2, and starts at 0. So it's 2 over 5 seconds. So that would be the acceleration. And we weren't able to draw exactly what the graph will be just from the graph. We would need more information. But if we assume this is the correct velocity versus time graph, this would be the acceleration. So that means all the way up till 20, this whole graph will be at 0. And then out here, it will be at 2/5, which will be somewhere around here. And that'll be the acceleration versus time graph. Alright, one final thing is the velocity versus time graph and some questions with that. So this can be pretty tricky, I think, and it can take some getting used to understand how to read these graphs and like what are they actually showing. So let's go through some examples. So we see Bob's traveling, giving the velocity time graph shown above. Alright, so when is Bob traveling in the positive and negative direction? So this is the same kind of thing we did with the position graph, but now we're given a velocity versus time graph, right? So when we were on the position versus time graph, we just need to find where the slope is positive, which is when the velocity was positive. So if we're trying to find when Bob is traveling to the positive direction, we can simply just find where is the velocity of positive versus negative. So this is when velocity is positive or negative. Alright, so I'll just denote positive here and we can write these in. So that means that during this whole first segment, this is all the positive area. It's all positive here, right? So that means that from time 0 to time 11, Bob is traveling in the positive direction. Seconds. Okay. And then from 11 to 22 is all in the negative direction, because now the velocity is negative and the speed he's moving at is now in the negative direction. So from 11 seconds to 22 seconds. And then this final point, it switches back to going in the positive direction from 22 to 27. Alright. Okay, so now we need to find what is Bob's displacement from 0 to 9 seconds. So displacement, how are we supposed to find displacement using velocity? We know how to find acceleration, it's just a slope, but how do we go backwards? How do we go from velocity to displacement or position? And to do that, we have to find the area. So if we wanted to find the displacement from 0 to 9, we would find this area under the curve right here. So this area will equal the displacement. So let me set this up so we can see. Okay. So we basically just want to find, this area. So we can do a little bit of geometry here and find that the change in x is equal to 1/2. We'll just do these as separately as like a triangle and a square here. So 1/2 the base, which is 4, times the height, which if we denote each one of these as 1, that is also 4. And know that these are in, let me draw out the units actually, because I think this will help prove that the area is the displacement that the units work out. So the 4 is seconds times 4 meters per second, plus this square here, which is another 5 seconds times another 4 meters per second. So these seconds will cancel out and we'll just be left with meters. And if we plug all these into a calculator, we get 28 meters. And also note that this is a positive 28 meters because these values are all positive. And if you were to get negative, it would be in the negative direction, and that would be the displacement in the negative direction. Okay. Alright, so when is Bob slowing down? Alright, so where is he slowing down? So this is, I think, was most tricky for people, because it's not as easy to tell when is he slowing down, because it's not just negative, positive. You might think, oh, when it's negative, but here it's in the negative direction. It doesn't mean it's going down. So we want to look at when is the velocity, when is the speed decreasing. So if we look at this first point, the speed starts at 0 and ends at 4. That means he's speeding up. At this point, there is there's no change in the velocity, so the speed will just be remaining constant. But from this 9 to 11, he starts at 4 and ends at 0. So this speed is decreasing. But from 13, his speed is now back up to 4 in the negative direction. But that means that he's speeding up. So this is slowing, and this point is speeding up. But at this point here, the velocity is 0. So that when this is going here, it's also slowing down. And so you can think about it as like you have a car that's going in the negative direction, and or actually to make this work for this graph, for this point right here, the car is going in this positive direction, but it's slowing down. So it gets slower and slower until it stops, and then starts speeding back up in the opposite direction. So only this point from 9 to 11 and from 13 to 22 is it slowing down. And so for a rule of thumb, it'll be slowing down if it's going towards the x-axis. And if it's going from away the x-axis, then it is speeding up. So it's slowing down from 9 to 11 and from 13 to 22. So I'll just write that in. 9 seconds to 11 seconds and 13 seconds to 22 seconds. Okay, and finally, what is the acceleration from 13 to 22? So we already know the acceleration is the slope of the velocity graph, so we can do the average acceleration equation of this right here, which we already found that the final velocity was 0 minus the initial velocity, which is a negative 4, over a time of 22 minus 13, and that will give us 4 over 9 meters per second squared. So that'll be that velocity for this point. Alright, so that's everything for graphs. These are really important and can definitely be tricky, so definitely do more practice on that. If you have any questions, let me know in the comments. And yeah, have a great day.